Well, welcome everyone to this week's edition of the HoloTube seminar series. We are very happy to welcome Andreas Karch from UT Austin now, and he's going to tell us about his explorations of continuum quantum field theories of fracton order. Take it away.
Thank you very much for giving me the opportunity to speak here. What I want to talk with you about today, that was my warning slide you already see now, this is supposedly a HoloTube talk, but there's going to be no holography in this talk. I always exclusively going to talk about quantum field theory, but maybe the excuse of doing this here is you could wonder whether wouldn't it be nice to redo some of the things I'm going to tell you about today in holography. I'm not really sure how useful this would be, but it's definitely something one could explore. The main lesson I want you to take away from today's talk is that fractons, and I'm going to explain a little bit more what this is, may force us to rethink long-held beliefs about quantum fields. And before I delve into this, let me kind of review some of what I think are these long-held beliefs that many of us have about quantum field theories that we might have to sort of at least partially abandon because of fractons. But there's this idea that quantum field theory is sort of the universal language of physics, where it doesn't really matter what you want to describe. You can describe like a solid or maybe universe. Is down here sort of a picture of like a Calabi-Yau, six-dimensional internal space over a four-dimensional Minkowski space, and your internals, your solids could be made out of spins, out of atoms. No matter what your microscopic description is, when you zoom out and describe the system at length scales, which are much, much larger than sort of the microscopic length scales that sort of, describe degrees of freedom that make up your system. The idea is like at long distances, this is going to be all described by some sort of quantum field theory. And the quantum field theory, you're organized by some sort of low energy expansion. You do a derivative expansion. You end up with a continuum quantum field theory, which furthermore is determined by just a few low energy constants. And this way, continuum quantum field theory becomes sort of the universal language for like a host of different phenomena. It can be fundamental physics, particle physics, condensed matter physics, you name it. In the end, at long distances, it's just going to be some continuum quantum field theory. In particular, if we want to end up classifying sort of all possible phases of matter, what could happen? You have like this very simple flow chart. First, you have to decide, well, is your system gapped or not? Is there an energy gap or not in the system? If there's no gap, then at long distances, you get some sort of conformal field theory. And if it's gapped, then there's still some question of whether there's some non-trivial ground state degeneracy. If not, then you have an entire triple theory. It's very easy to describe it. You just write Lagrangian is equal to 1, and there's absolutely nothing happening. If there's some non-trivial ground state degeneracy, then you can have topological excitations, and typically are described by some non-trivial topological field theory. But lo and behold, you would basically end up with the statement that we want to understand all possible phases of matter, and here matter includes again sort of the universe as a whole. All you need to do is sort of classify all potential topological field theories and conformal field theories. And, you have, when you talk about the CFTs, there's some disclaimers you might want to make of kind of whether it's relativistic or not, and there might be some non-trivial scaling, but one way or another, that's sort of what we all thought is the task. If we want to understand everything that could be out there at long distances, all we have to somehow do is understand topological field theories and conformal field theories. That's sort of the Wilsonian paradigm. You organize physics by scales, and then long distance scales, there's only a few options, or a limited number of options that you can possibly write down. And fractons sort of call this entire idea into question. Fractons do have a large ground state degeneracy, but they are not topological. And the fact that they are not topological, you can see from just observing how many ground states there are. The number of ground states grows with the system size, right? So system size depends on geometry. It's not a topological field theory. Furthermore, they have excitations with limited mobility. For example, excitations that can only move along lines or planes, which is also something we haven't heard of in standard quantum field theories. And maybe, from the theoretical point of view, what's going to turn out to be maybe the most important thing is they have subsystem symmetries. And I want to talk more about what exactly it is. So whenever a new discovery contradicts dearly held theoretical beliefs, our first idea would be to blame it on an experimentalist. Surely somebody must have made an error. That can't possibly be. But the problem is fractons are purely theoretical construct, right? We can't blame it on experimentalists. It's kind of theories fighting with theories. At this stage, what fractons are solvable lattice models. So we know all these properties that I wrote down on the page before. We know those as facts because unlike many interacting quantum field theories, these lattice models, we have exact understanding of their spectrum, their ground state degeneracy, their excitations. And they have these features that I wrote on the page before. And so we have these lattice models, which don't seem to have any viable long distance description in terms of a standard quantum field theory. Of course, I'm going to tell you that they do have proper long distance descriptions by now, but these will be not standard quantum field theories. We have to sort of change the rules of what we leave a quantum field theory. But before I get there, I wanted to at least review for you like one of these simple fractons models, and that's sort of the X-cubed model. That wasn't the first one, but that's the one that's easiest to explain. This is a very simple lattice model where you just your basic degrees of freedom are basically Ising spins. Maybe different from the standard Ising model, these Ising spins live on lattice links, not on the sides. But like in the Ising model, we only have interactions between nearby spins. And at some level, this is a generalization of Guittard's toric code. You can think of this as being coupled layers of toric code. Okay. So here's the Hamiltonian. The Hamiltonian is a sum of terms, and there are only two types of terms in there. The first term is where this model got its name from. It's like a bunch of sigma x's. So big X stands for the sigma, the Pauli X matrix acting on the spin on a given link. And I have a product of sigma x where I multiply sigma x along all the edges of a cube. So there are terms which look like sigma x's on the edges of a cube. And the second type of term is this cross term that I denoted by A. So this is like you take a cross which has like 4 links, right? So this is a 3D model, but I only have these cross terms always live in planes. So I have crosses associated with the xy plane, the yz plane, and the xz plane. So there are 3 types of crosses. And I take 4 of the sigma c's on like the links of a cross and multiply those together. Then of course I sum over all possible cubes. And for the crosses, I also sum over all possible orientations. So all 3 orientations and then summed over my entire lattice. What's special about this Hamiltonian, it's a type of Hamiltonian known as a commuting projector Hamiltonian. Basically, the important thing is that all terms in this Hamiltonian commute with each other, right? Obviously, B's commute with B's and A's commute with A's, since X's commute with themselves and C's commute with themselves. And then if you ask yourself about the commutator of an A with a B, there's obviously the opportunity for things to not commute, since when you commute X via past C, you get a minus sign. But if you look at the structure of those, every cross shares exactly 2 links with like nearby cubes, and far away cubes, they share no links. So you always pick up 2 minus signs when you commute an A through a B. So in the end, every A commutes with every B. So because my Hamiltonian is just a sum of commuting terms, you can find the ground state by just simultaneously diagonalizing all of them. So ground states in the system are states which are a simultaneous eigenvalue -1 under all A's and all B's, assuming I have positive couplings. Right? So I minimize my energy by having eigenvalue -1 for every single term in the Hamiltonian. These are all like terms which have like square root of 1, so they have eigenvalue +1, -1. So I want to have -1 for every single one. Well, it tells me that the spectrum is gapped, because if one of those terms has eigenvalue +1, then I have a finite energy difference to the terms to the ground states which have eigenvalue -1. Above the ground states, you have excitations, and excitations you get when you kind of sum of those terms where you have eigenvalue +1. And you can write down these excitations by acting on a ground state with like a set of sigma z's and sigma x's. So on the left-hand side, I showed you like an excitation on the ground state where I acted with sigma z's along. You can think of this as being a membrane that's sort of intersecting the links. But what's really denoted here is like these red lines, where I have a red line, they acted with sigma z. So I flipped the x spin. So whenever you see a cube that has an odd number of red lines, that would be something where I flip the eigenvalue from -1 to +1. And that's something where I have some non-trivial excitation. So you see the cubes in the middle, they have 4 red links, so they're fine, they're still in the ground state. The cubes on the side, they have 2 red links, they're still in the ground state. But the 4 cubes in gray at the corner, they have 1 link flipped. So those are the ones where I violate my commuting projector Hamiltonian, where an eigenvalue got changed from -1 to +1. So this is an excitation where I kind of raised the energy sort of by 4 units, and I created 4 excitations. And these are these limited mobility excitations that I talked about before. Clearly, I can kind of make this sheet longer in sort of the direction where I wrote it down, right? I can take like 2 of those gray excitations and move them as a pair in the plane in which they're living. So if within the plane in which they're living, they can move as a pair. I can either move like the pairs this way, or I can move a pair down. If I try to move a single one of them, say if I take the gray cube that's sitting in the top corner and replace it by a red cube, I would be adding 3 more red links. You might have thought, well, what it did, it moved the gray cube up. But at the same time, what it did, it created 2 cubes which have now 3 red links, and 3 is also an odd number, so they would also be violated. So in the process of moving, trying to move one of those fractons, or this is sort of what people sometimes call a planon, because it can easily move in planes. If I try to move one of those planons up, I secretly created 2 more of them. So instead of just moving one excitation, I pair created 2 new ones. So these planons cannot move in isolation, and you'll find something very similar if you try to move them out of the plane. If you try to move a pair out of the plane, you also, instead of moving the pair, you would end up creating a new pair. And then very similar for the lineons over here, the blue line, which I get by acting with sigma x's. So the sigma x's now violate some of the cross terms. And in the middle, so like all these links where the line crosses through, I have crosses which always have like 2 links that got changed, so nothing happens there. But the links at the end, or the last link has only 1 link change at a given cross. So I created 2 excitations at these 2 black dots. Again, I obviously can move these excitations within the line by just acting with more sigma x's, but I can't move them transverse to the line. If I were to try to move them in a different direction, I would end up creating 2 more of those rather than moving the ones that I had. Here's maybe what will be the most important for us from the point of view of the continuum field theory. One more properties of these of the X-cubed model, and that it has a subsystem symmetry. So like in any standard Ising spin model, since everything, all the terms in the Hamiltonian only rely on the relative orientation of the Ising spins. If I take all the spins and flip them, so do some overall spin flip of every single spin in my system, clearly that's a symmetry of the system. And the X-cubed model, what you can do is you go in and pick any plane, and this can be an XY plane, a YZ plane, an XZ plane. You take any plane and flip all the spins along that plane only. So not all the spins in the entire cube, but only all the spins along a plane. That also commutes with the Hamiltonian, all the terms in the Hamiltonian. And so that's also a symmetry. And that's called a subsystem symmetry, because there's a symmetry operation which, unlike a global symmetry, which acts on the entire system, only acts on a subsystem.
I have a question, if I may.
Yes.
So you have to take a plane, but you cannot deform that plane, right? It has to be a flat plane, is it?
Yes, yes. It's not like sort of any 2-dimensional submanifold. It's a plane. It's like a plane. So there's something about the underlying lattice structure that's sort of remembered by the subsystem symmetry. It needs
so should I think of each transformation on each plane as separate symmetry?
Yes.
Okay.
Sort of not a slide I'm having right now. The symmetries basically explain to you right away why you get this weird ground state degeneracy. In fact, every plane actually has 2 C2 symmetries, and the second one is like a magnetic one. It's sort of, if you think of every plane as being a toric code, the toric code has a C2 times C2 symmetry. But one C2 symmetry is much easier to see than the other one. But you have the C2 symmetry, it's a gapped system. The C2 symmetry gives you basically a 4-fold ground state degeneracy on every single plane. And then the total ground state degeneracy in the system is simply 4 times the number of planes. And how many planes do I have? I have like 2 LX. I have LX planes, LX YZ planes. I have LY XZ planes and LC XY planes, where LX, LY, LC is the number of lattice sites in the X, Y, and Z direction. And then there was some redundancy. I was over counting. There's some -3, because if you look at the full C2 symmetries, there's some sort of global constraints. But in the end, you get a number of ground states that's sort of extensive in the system size. It's not extensive in the volume, but sort of the log of the ground state degeneracy grows linearly in system size. And that's basically a direct consequence of the subsystem. So the important thing about all these things is this doesn't sound like any quantum field theory we had ever seen before, right? The fractons do not allow a field theory description in terms of a standard quantum field theory, right? I think clearly we don't want to give up the Wilsonian paradigm, right? The Wilsonian paradigm is just so beautifully organized physics by scales, and then in the continuum limit at very long distances, everything should be some sort of quantum field theory. But we do have to admit things as quantum field theories which we probably didn't want to think of before. We have to broaden our notion of what a quantum field theory is in order to allow fractons to be described by our framework of quantum field theory. And there are two sort of approaches that people took to describe, write down quantum field theories for fractons. And they're sort of, the first one sort of gets you halfway there. Right? They basically say, well, look at this, every subsystem is a toric code. We know how to write down quantum field theories for the toric code. It's just some sort of C2 gauge theory. And so what I do is on each layer, let me take a standard continuum limit, and then the subsystem symmetry just acts on the layer, and then I take a lattice of 2 + 1 dimensional field theories. So it's a continuum field theory in the sense that my Lagrangian involves sort of continuum field theories in 2 + 1 dimensions, but then the third direction to get up to my 3-dimensional cube model, I latticeize the third direction. This goes sort of by the name of foliated field theories. It strictly speaking involves continuum quantum field theories, but one direction you sort of leave latticized, and that alone immediately tells you, well, you sort of still count the number of planes. Each one of these continuum field theories gives me some sort of topological ground state degeneracy, which only depends on the topology of the slice. I end up getting like some sort of discrete, many of those have one direction with latticized, and that's where all the interesting properties come from. You can try to go one step further and say, this isn't really what I meant by a continuum quantum field theory. There's still one direction that's sitting on the lattice. So there are now continuum quantum field theories that people can write down. They have a subsystem symmetry, which I think from the quantum field theory point of view, this is sort of what drives most of the interesting properties. They have a discrete rotation symmetry. We are very used to that continuum quantum field theories have a continuum translation symmetry and a continuum rotation symmetry. That second aspect is something you have to give up. And as a consequence of those two features, the subsystem symmetry and the discrete rotation symmetry, you'll find that these quantum field theories, even though they look like continuum quantum field theories, they retain some sensitivity to lattice scales. All these funny underlying purely geometric properties like that, it's special that the XY plane isn't the same as any other two-dimensional submanifold. That the quantum field theory remembers this. If you write down Lagrangian, which looks completely innocent, it looks like it's a genuine quantum field theory written in a continuum, has nothing to do anymore with the lattice. The moment you start calculating pretty much anything, you get the lattice spacing like jumping right back at you and saying, no, I'm here, you can't forget about me. Okay, let me discuss one of these field theories, right? It was first written down by Paramekanti, Berlins, and Fischer, but it got popularized recently by Seiberg and Shao. And so I'll refer to this field theory and all field theories in its Inc. as Seiberg-Shao series in a sort of abuse of history. So here it is. It's a free scalar field. It has a standard time derivative term, d0 phi squared, but what's new is that its gradient term is not just the x phi squared plus dy phi squared, but it's the x dy phi squared. Okay. So this is now a 2 + 1 dimensional theory, and it's also gapless. So clearly more bells and whistles are needed for the x cube, but Seiberg and Shao also wrote down a gap theory that actually describes this x cube model that I wrote down before. It is a continuum quantum field theory in the sense it has continuous translation invariance, right? So that's sort of what makes it a continuum theory. It has a continuous translation symmetry. It no longer has a continuous rotation symmetry. It's only invariant under 90-degree rotations, right? These are the rotations of a square lattice. The symmetry of a square lattice is the only rotation symmetry you see. So x goes to y, y goes to minus x. That's a 90-degree rotation. The x by dy goes into minus itself, and the x by dy is squared, is invariant. It has a subsystem symmetry, which was one of these defining features of the fracton system. A free scalar field has a shift symmetry, but because of this new type of gradient term, it has a shift symmetry where I don't just have the ability to shift my scalar field by a constant, but I can shift my scalar field by an arbitrary function of x only, or by an arbitrary function of y only. And it's very clear from looking at the structure of the gradient term, because I have the x and dy, a function of only one of the two variables doesn't affect the x by dy, the x dy are fine. The way you should think about this is if you have a different shift symmetry of different x's, what x is basically labeling, the coordinate x labels lines in the y direction, right? If every line in the y direction is sitting at a different x. So this is exactly a subsystem symmetry in the sense that it acts. This constant that depends on x is saying I can shift the scalar field along a line in the y direction. And I can choose a different constant at different lines. In particular, I could choose like this constant to be a delta function in x, which is saying I pick a given line in the y direction, and shift the scalar field only on that line. And now, like in the X-cube model, is crucial. You can't just choose some random diagonal line. It has to be a line in the Y direction or a line in the X direction. You can't have anything mixed. This theory is free, right? It's quadratic and phi's. And in fact, if you try to write down any interaction term from this Lagrangian, you can't, at least if you want to stick to marginal and relevant interactions, right? And any interaction, in order to respect the subsystem symmetry, has like the x dy phi acting on phi or the 0 phi, and then you end up automatically with something which has higher dimension. So even though this described an interacting theory on the lattice, you get a free field theory. So it's not that easy to write down continuum quantum field theories which have the subsystem symmetry. So interacting with one scalar field, and as I just said, you can't write down any interactions, but later we'll see some theories that have interactions where I add some extra fields to this one. Here's maybe the most interesting thing about it, and this is where this sensitivity to the lattice scales comes in. If you analyze the dispersion relation purely classically, right? If you solve the equations of motion for this theory, you find that the energy is basically given by kx times ky. And this has some really dramatic consequences, right? What this is telling you is you have some strong mixing of your V and IR degrees of freedom here. You can have arbitrarily short distance modes in the Y direction. So you make ky as large as you want. So this is saying you have arbitrarily large momentum in the Y direction. You have like arbitrarily strong discontinuities in the Y direction. In particular, you can study field configurations where on different x lines, so you have one line in the x direction, and right next to it, you have a different line in the x direction. The field values are not related whatsoever between different lines in the x direction. You can have arbitrarily discontinuous field configuration, discontinuous in the Y direction. As long as they're smooth in the x direction, they're low energy. So we are used to the fact in the quantum field theory, the insensitivity to the lattice scale comes about because if I have kind of arbitrary, strong discontinuities, if I have jumps at the lattice scale, they would have very large actions. And so they're suppressed in my Pearson curve. This isn't happening here. You can have arbitrary low energy with arbitrary sharp discontinuities in one direction as long as they're smooth in the other. And if you look at the Hamiltonian for the system, again, this is a free series. So you can just solve the Hamiltonian analytically. You see, for example, one thing really peculiar that's happening is these would-be zero modes. So I have these modes which seem to have arbitrary strong jumps in one direction, but have zero energy because they're smooth in the other directions. These would-be zero modes, they're actually lifted by quantum effects, and they get a mass which instead of on energy, which instead of being zero, ends up being up at the lattice scale. So you have a continuum quantum field theory, but because it allows arbitrarily sharp discontinuities in the field configuration, it retains a sensitivity to the lattice scale. In particular, modes that classically look like zero energy end up having energies of order the lattice scale. So this is a new set of quantum field theories, right here, these quantum field theories which are different from anything we've seen before. And I really think the rules of what a quantum field theory is have changed by, these look like very innocent quantum field theories, but they behave very differently from anything that we've ever seen. So we have a brand new playground, and at this level, I just so let's go play and let's see what we can do with these new type of quantum field theories. Here's a long list of things I could talk with you about today, things I've been really recently entertaining myself with. And it's the first three that I picked for today that I want to expand on a little bit more. Any questions so far? So this was my introduction of why I want to study quantum field theories associated to fracton order. And now I'm going to tell you about three particular projects. Right? If nobody has any questions, then let's jump right in and talk about subsystem conformal field theories. Right? So these are three series. So you might wonder, do they have conformal symmetries? And if so, what is their structure? But before we talk about conformal invariance, let's first talk about scale invariance. One thing really interesting that's happening in this action is that it doesn't have just one scale symmetry, it has two scale symmetries. And I can look at this free Lagrangian and I see that if I rescale time, I can either compensate this by rescaling x, or I can compensate it by rescaling y. I don't need to do both. In the standard quantum field theory, I'm used to that scale invariance rescales all coordinates, it rescales time, sometimes with different weights. But here what you're finding is a scale symmetry in xt, and you're finding a scale symmetry in yt, and they can act completely independent. The scale invariances I have these two different scale symmetries, xt and yt. So I have the two different two-dimensional scale symmetries in my three-dimensional quantum field. Can these be extended to conformal symmetries? And the answer we found is yes. And one easy way of seeing this is a kind of doing it, going to Fourier space in one coordinate, but not in the other. So if you go in Y, you go into Fourier space, and in different Fourier modes completely decouple. So you get Fourier mode by Fourier mode. You end up with a 1 + 1 dimension series that's living in the X direction. And that is just a free scalar in 1 + 1 dimension. That's a standard relativistic conformal symmetry that you're having in the X direction. So this dx, the scaling in the X direction, where you rescale X and time together, that's part of a standard relativistic conformal invariance in X and T. And similar for dy. So the system has two conformal invariances, one in xt, one in yt. And furthermore, those don't commute. And you end up with infinitely many additional generators that you need in order to close the algebra. And so you have this very complicated conformal structure where you don't just have basically two Kurosawa symmetries, but you have two Kurosawa symmetries which don't commute and generate a whole slew of new generators. While in this system, you end up with some infinite dimensional algebra, which you don't even know how to exactly write down. There are simpler models you can write down where you can work out the full algebra, where you still have two different conformal symmetries. And they kind of, you need to add a finite number of generators in order to close the algebra. So there's some very interesting conformal structure there, and depending on the details of the example, you sometimes get infinite dimension and sometimes get finite dimension conformal algebras. But you have always these subsystem conformal symmetries where you have conformal symmetries which act like only on part of the space. Okay. The thing which I wanted to talk most with you about is spontaneous symmetry breaking. That's sort of my most recent project on this. And this goes back to the question, if the subsystem symmetry is so important defining this theory, right? The subsystem symmetry is really what was driving all these novel features, right? The subsystem symmetry is what allows you or what forces you to consider this discontinuous field configuration. What can we say about their breaking? Can subsystem symmetry be spontaneously broken? And what are good diagnostics? Do we have some examples of quantum field theory where subsystem symmetries are spontaneously broken? First, let's start with a theory that has actually been analyzed a long time ago by Batista and Nusinov, who showed you that basically the theories that govern subsystem symmetry breaking are just some almost trivial generalization of the famous like Mermin-Wagner theorem. But basically, if you want to know whether a subsystem symmetry that acts on a d+1 dimensional subsystem defect, whether that can be broken, the same rules apply then for quantum field theory, which would just genuinely live in d+1 dimension. So what Mermin-Wagner is telling us that if you, for example, want to break a continuous symmetry, by the subsystem symmetry I wrote down for you in the simple Seiberg-Schau theory, we have a shift symmetry that's a continuous symmetry. We know that in ordinary quantum field theories, continuous symmetries can only be broken in 2+1 dimensions and up. So this is telling me when I have a subsystem continuous symmetry, it can only be broken if the subsystem is 2+1 dimensional or different dimensional. In particular, this 2+1 dimensional Seiberg-Schau theory that I discussed so far, that has a subsystem symmetry that was acting on lines, right? Lines, that means 1+1 dimension. So this subsystem symmetry cannot possibly spontaneously be broken. But you can write down higher dimensional generalizations. In 3+1, you have choices. So here's an unwise choice where you generalize Seiberg-Schau in the obvious way. Instead of writing dx dy phi, you write dx dy dc phi. That now has a subsystem symmetry where I have shifts which can depend on y, z, cx, and xy. And if you think of this carefully, right? For example, if you think of the last one, I have a shift symmetry that depends on x and y, right? A pair xy basically labels a line. This shouldn't read the x direction, but in the z direction, right? So again, the subsystem symmetries, because they depend on two coordinates, is telling me they act on codimension 2 defects. So even so I wrote down a 3+1 dimension field theory, these subsystem symmetries, they still act on lines, so they cannot be broken. But you can generalize this pattern. Instead of writing down this Seiberg-Schau theory with 3 derivatives, you can write down something where you write down all possible 2 derivative terms in 3+1 dimensions. So now I have only a shift symmetry where my shift can depend on one coordinate, on x only, y only, and z only. So this time this characterizes planes. So this gives me a continuous subsystem symmetry that's acting on planes. So in principle, it could be broken. Alas, it isn't. Right? Theorems just tell me whether something could be broken. Seiberg and Schau tell you the subsystem symmetry isn't broken. Let me quickly tell you 2 arguments how you can see that the subsystem symmetry in this case actually isn't broken. And then we try to move on and see whether we can do find systems that actually break the subsystem.
I have a question before continuing, if I may.
Okay.
How should I then understand the huge degeneracy that comes there? Usually we understand degeneracies as some symmetry being spontaneously broken.
The ground state, the ground state degeneracy, to get these huge ground state degeneracies, you need to look at the gap systems. When I described to you the discrete model, I did the X-cube model, which is a gap system, has a huge ground state degeneracy. Now I moved on to the simple fracton field series, which are continuum quantum field series, which are gapless. These gapless systems, you don't have much ground.
I see.
If you want to describe the X-cube model, basically, so here's like a scalar, which has subsystem symmetry. Seiberg-Schau also wrote down gauge fields, which have subsystem symmetries. And for these gauge fields, if you write down something like a BF action, a topological field series about gauge fields with subsystem symmetries, those are the ones which reproduce these large ground state degeneracies.
Right. So in those cases, is the subsystem symmetry discrete? Is that the point? And then it avoids the Mermin-Wagner theorem. Is that how? In
these cases, the subsystem symmetry ends up being discrete. Yes.
Right. So then Mermin-Wagner analogs don't apply. I see. Okay. Thank you.
So yeah, my motivation example and the field series I'm discussing was like, I gave you the simplest lattice model, now I'm discussing the simplest quantum field series, and they're not directly related. But there are quantum field series that also describe the X-cube model. It's one of the few, or one of the fractal models for which people do have a good quantum field series. Yeah. Let me look at why in this particular continuum quantum field series I wrote down the subsystem symmetry. When I first studied, the subsystem symmetry isn't broken. That goes back to this fact that these modes got pushed up to infinite energy, right? If you have, right, this is the subsystem symmetry is a global symmetry. So you might expect a broken symmetry should give rise to Goldstone bosons. So we are looking for zero energy modes that are protected by the shift symmetry. Naively, that's exactly what we wrote down. We wrote down the theory of free scalars. The action is protected by the shift symmetry. And we found we have this large number of zero energy modes. We have the zero energy mode where either Kx or Ky is zero, right? These naively seem to be exactly the Goldstone bosons that will correspond to a spontaneous breaking of subsystem symmetry, right? The fact that my field phi doesn't phase rotate, but it shifts, so the subsystem symmetry is non-linearly realized, and I have a large number of massless modes, right? That looks like this should be the Goldstone bosons. And then the fact that these Goldstone bosons their energy gets pushed up to the lattice scale, that's sort of the first indication that the symmetry that looks broken at the classical level, in fact, quantum mechanically gets restored. The would-be Goldstone bosons have an energy that gets pushed up to the lattice scale. Then, other diagnostics you might want to write down, and they might look cleaner, even so the answer you're going to get isn't all that clean, right? But typically, people would tell you maybe the most reliable diagnostic of symmetry breaking are correlation functions. You write down a symmetry neutral correlation function where you take two charged operators in a combination that in the end you get a neutral correlation function. You calculate this correlation function in the limit that these operators are widely separated. And then the statement is if that in this separation goes to infinity limit, if the correlator goes to zero, you would say the symmetry is unbroken. If the correlator remains non-zero, the symmetry is broken. And the intuition that goes behind this is that by cluster decomposition, you would be saying that at large separation, this two-point function beta factorizes by locality, and then a non-vanishing correlator for this neutral two-point function indicates to you that these charged operators basically got a vacuum expectation value. That's typically the easiest way to detect symmetry breaking or not, is to look at the correlation function and study the large distance limit of the correlation function. Yeah, let's try to do this in this Seiberg-Schau series. Because we have the subsystem symmetries, the simplest charge neutral correlation function you can write down is this time not a two-point function, but a four-point function. You want to have something that's in the end is charge neutral, so I can write down this exponential of four scalars where I basically organize them along a square. And that's now invariant under my subsystem symmetry. And then I want to study the long distance behavior of this correlation function. So I want to take my operator insertion, separate them in the x1 direction, and I separate them in the x2 direction. The way I'm going to analyze my answers is I write this as e to the minus 2k. Right? What I'm going to, in the end, going to plot you is only this exponent, which I call k now. And then for my other examples, I'm going to call it I. But sort of what we want to see is that the separation goes large. Does K go to something finite, which would be an indication of symmetry breaking, or does K go to infinity, which would be an indication of the, the correlation function vanishes, so symmetry is unbroken. The theory was Gaussian, right? This is a free theory. I'm calculating some complicated correlation function, but in the end, I can do this all by big contraction. And long distance behavior is telling me whether my symmetry is broken. Again, we're looking for a diverging positive K as a sign of an unbroken symmetry. So here's what you get if you do this in the simple Seiberg-Schau theory in 2+1 dimensions. You get some sort of diverging integrals by just writing down this 2-point function. You can try to regulate them by some UV cutoff. I have also some mu and mu naughts, which I didn't write down before, but this would be if I give the coefficients of the kinetic terms, the time derivative and the space derivative terms. If I give them some arbitrary coefficients, mu and mu naught, they show up in my calculation. And I have these cutoffs, lambda x and lambda y. And what's so peculiar about this calculation is basically they show up in this combination log x lambda x times log y lambda y. What this is telling me is that the cutoff in the y direction lambda y shows up together with a position dependent log x term. So I can't do a standard UV regularization where I have a lambda y and the lambda x, which I just once and for all introduce. I get position dependent cutoff dependent terms. And this is sort of how in this trying to do a standard QFT calculation, this UVIR mixing would show up. The way you regulate the UV divergences in Y depends on long distance properties in X, right? The large separations in X give me different cutoff procedures in Y. This also reflects the fact that on the spectrum analysis, the lightest charge excitations got pushed up to the lattice scale. So there's no standard UV regularization you can do in order to give you a well-defined answer for this correlation function. Here's the words people would say about this, right? This correlation function K is intrinsically divergent. There's no meaningful finite value you can assign to it because I cannot regulate my answers by just putting like a position independent UV cutoff on my system. People take this as another indication that symmetry is restored. Again, there's no meaningful finite value I can assign to this integral. So the only meaningful value I can assign to it is basically e to the minus infinity, which is 0. It definitely shows you there's a significant UV-IR mixing, right? The UV cutoff depends on the IR properties in the other direction. And exactly the same results hold in other dimensions. If you take any of these higher dimensional generalization of the Seiberg-Schau theory, you find that there's no consistent UV cutoff scheme you can impose that allows you to assign a finite value to these correlation functions. And together with the analysis of the spectrum that already indicated that the Goldstone boats get pushed up to infinite energy, people would tell you this is another indication that you have no symmetry breaking, even in the systems where this allowed, where subsystem symmetry lives on. So given all that, you might wonder, is there maybe some other theory I can write down that gives me spontaneous symmetry breaking? There are these Coleman-Wagner-like theorems that tell you spontaneous symmetry breaking should be possible as long as you have planes. And here's a theory we analyzed that actually works, and it looks much more easy to analyze than these original Seiberg-Schau theories. We call this the classical XY model. This is basically the same action I wrote down before, except for this one time I don't have the d0 d phi term. Right? It's only the spatial gradients where I have the x dy phi squared. There are two ways you could view this. We call it the classical XY model because you can take exactly the same lattice model we had before that gave rise to this 2+1 dimensional Seiberg-Schau theory, this XY model. I didn't talk about that lattice model, but there's some underlying lattice model you can write down, which is known as the classical XY model. You take the same lattice model, but instead of studying it at a quantum phase transition at 0 temperature, you will study it at finite temperature and do some sort of statistical analysis with this, right? You write down the Hamiltonian that would allow you to write down c to the e minus beta h. You study it as a classical statistical model, and you would write down the same Lagrangian just without the time derivative. You can Wick rotate one of those spatial coordinates into a time coordinate, and then you would say, I can also think of this as being some peculiar continuum quantum field theory. At this time, not only do I get non-trivial gradient terms, this time also my time derivative terms are interesting. Right? My time derivative terms, I don't have d0 d phi squared, but I have d0 dx phi squared. Right? I have all my time derivatives are always accompanied with one other spatial derivative. I don't have d0 phi squared alone, but it's always d0 di phi squared. I now have also a subsystem symmetry in the time direction. So you can view this either as a Euclidean theory standard StatMech model, or you view this as a Lorentzian symmetry with a subsystem symmetry. The shift is parameterized by time, not by space. In any case, this has a subsystem symmetry, and my subsystem symmetry lives on codimension one space-time manifolds, right? Because my shifts can depend on any one coordinate. So symmetry breaking should be allowed whenever I'm in more than 3 space-time dimensions with this classical experiment. Again, I have a subsystem symmetry. I write down a 4-point function. That's the simplest neutral correlation function I can write down. I write it as e to the minus something in the exponent. So we want to know whether this exponent goes to plus infinity or whether it remains finite. So again, you can do this just by Wick contractions. You get this integral up there. And if I do this with d equals to 2, so 2 space-time dimensions, you get a very simple expression. Xy goes to infinity as either one of those coordinates goes to infinity. So the symmetry is restored. And I diverges to plus infinity. I have no symmetry breaking. This had to be the case by this generalized Merman-Wagner theorem. Remember, I need to be at least in d equals to 4. But now if you do the same for d equals 3 and d equals to 4, here's sort of how these correlation functions look like. I plot them as a function of one coordinate x for various choices of the separation, the second coordinate y. And you see in d equals to 3, my correlation function, the exponent in my correlation functions, it diverges logarithmically, but it still diverges. It goes to plus infinity. So symmetry is restored like it had to be by the theorem. But then in d equals to 4, at large separation, my exponent goes to something constant. And again, that's exactly a sign of my symmetry being spontaneously broken. So this classical XY model with d equals to 4 is sort of an example of a symmetry where subsystem symmetry is spontaneously broken. And again, you can analyze this in a free series. So these results are kind of completely solid. There's no question about interactions or anything. This free series displays spontaneous breaking of subsystem symmetry. Furthermore, you can write down generalizations of this same theory, where instead of having 2 derivative terms, you add like m derivative terms, and you can do this in any space-time dimension d. And basically, if I have m derivatives acting in my scalar field and I sum over all possible combinations, I always get sort of shift symmetries which depend on m-1 coordinates. So this gives me subsystem symmetries which live on codimension m-1 dimension manifolds. This generalized Coleman-Wagner symmetry tells you that symmetries breaking could happen whenever d is bigger than m+1. So that's sort of the condition for that my submanifold is 2 + 1 dimensions or larger. And we find that in this type of series, symmetry breaking happens whenever it's allowed. So you see that already at the level of free series, we get a very rich structure where we have sometimes spontaneous symmetry breaking, sometimes we don't. And we can exactly calculate it because we have complete control over the series. Any questions about this before I move on to my last project, which is trying to talk about something other than free field sets?
I have a question, Andreas.
Good, go ahead.
Andreas?
Yes.
Usually I fear when I say usually in quantum field theory, your point is that these quantum field theories are somehow exotic, but I guess the question is, how do you do dimensional analysis in the type of field theory that you wrote down in order to decide, like, let's say, what terms are relevant or irrelevant or marginal? So
here we still have a standard scale invariance, right? I can assign on my field some sort of scaling dimensions. So I have standard scaling. I can do a standard scaling analysis. There's the fact that as UV-IR mixing, you might wonder what exactly, is there something beyond the scale analysis? But there seems to be, a standard scaling analysis that works fine in terms of, I wrote down these dilatation operators. I can assign everything eigenvalues. I know if I rescale on my lengths and my time, right? I have a separate xt scaling, yt scaling, but I can do the overall, the diagonal scaling, and I can write down for every field exactly how it scales under this. So I would still say rescale all my energy scales, my operator scale in a certain way.
I see. So you just have dimensional analysis with respect to multiple Ds. Yeah, that makes sense.
I could do separate ones, but the ones we're always doing when I do the scale analysis, when I use relevant or marginal or irrelevant, when I use these words, I always do the diagonal ones where we scale x and y the same way and then t accordingly. My next slide has a scaling analysis for an interacting field theory. Okay, not quite the next slide. Here I say some words, but probably the slide after that has the actual Lagrangian. Then maybe this will become more clear.
Okay, thanks very much.
Scalar by itself didn't allow any marginal relevant interactions, but you can write down series as multiple fields. Something many people looked at is like if you write down a complex scalar, right? You can think of what I wrote down, this would be Goldstone boson as maybe the phase of a complex field. If you write down action as the full complex field, you can get non-trivial interaction. But what we found is that sort of maybe the simplest theory of an interacting fracton is a scalar and a fermion coupled together. So I still have a single real scalar, and it has exactly the Seiberg-Schau scalar. But now I couple this to a non-relativistic fermion. And then my claim is in the system, there's exactly one interaction you can write down, and that interaction is multiple. So let's talk about how scaling works here, right? So since my scalar action shows up with one time two space derivatives, I basically want to rescale whenever I rescale space and time, I need to rescale time twice as much as space. So this is like a dynamical exponent equals to 2 scaling, which is also why I chose a non-relativistic kinetic term for the fermion, because it respects the same scale. So the weight, the Lagrangian has to have dimension 4 because dt has dimension -2 and dx dy has also dimension -2. So for my Lagrangian to have dimension 4, you see that the scalar field is dimensionless and my fermion has dimension 1. And that's sort of when we're talking about relevant, marginal, and irrelevant, that's the scale analysis we're doing. The one where I rescale time twice as much as space and then see how all my fields have to scale for the Lagrangian to be invariant. If you look at interaction, I get a dimension 2 from the fermion bilinear. If I had the scalar alone, because the scalar was dimension 0, the standard Yukawa coupling would be relevant, it has dimension 2, but the standard Yukawa coupling isn't allowed by subsystem symmetry. My scalar has to come with a dx dy, so I get exactly a marginal interaction. That's sort of the smallest interaction I can write down, and it's already marginal, so there's exactly one interaction with this. One thing you need to watch out for, usually you would say under rotations, the scalar is a scalar, it's invariant under rotation. In this case, my scalar actually has to transform non-trivial under C4 rotations. That's basically the x dy under C4 rotations because x goes to y and y goes to -x. The x dy picks up a minus sign. So I need my scalar to also pick up a minus sign under 90-degree rotation. It's in what people sometimes call the sign representation of C4. Right? But under 90-degree rotation, phi picks up a sign. So phi goes to -phi under 90-degree rotation. But with that, the system respects all the symmetries of the original Seiberg-Schau theory and has a single margin interaction. So you can say, great, that's just a standard quantum field theory. So I can do everything I always like to do in quantum field theories. I can calculate loop diagrams. So now we had this field theory, so we went ahead and calculated all the loop diagrams. There's like a wave function memorization for both the fermion and the scalar. And there's a vertex correction. And from this, you calculate the beta functions up to 1 loop order. And now while like the various kinetic terms in my Lagrangians and the chemical potential, they all sort of run normally, we find something really surprising, namely that the beta at 1 loop, the beta function for the coupling constant vanishes. And this is not sort of, you can't write down a diagram vanishing. No, you write down 2 diagrams, no, 3 diagrams in total, but 2 matter for this one. You get a highly non-trivial vertex correction. You get a really ugly integral, and why this doesn't have XY symmetries, you get really ugly answers. You get a really big long integral, and you get a wave function renormalization for the fermion. But then people will tell you the beta function for the coupling kind of picks up both a contribution from the vertex correction and from the wave function renormalization of the fermions. And lo and behold, those exactly cancel. You find that the beta function vanishes at 1 loop. That was at first very surprising to us. But I think we understand why there's a reason for this. This system, even so we engineered it to have a subsystem symmetry, it actually has some surprising new global symmetry. You can do the following. You go in and you kind of do it, instead of just having a phase rotation for that fermion, why that fermion is clearly invariant under like a U1 global phase rotation symmetry. You do a time-dependent phase rotation of that fermion, right? And because of the time derivative term that picks up, essentially that shifts the chemical potential, right? You generate a psi-dagger psi term in your action from that time-dependent rotation of the fermion. But you can compensate this by at the same time doing a shift in the scalar. And what you need is a shift in the scalar, which is x linear in x times y. Right? Before we had shifts in the scalar which only depended on x or only on y. Now I'm doing a shift in the scalar which involves a shift in x times y. And then you see, because my interaction involved the x dy phi, that also generates for me some sort of chemical potential-like term, a psi dagger psi term in the action. And then I can cancel the shift that I get from the time-dependent rotation of the fermion by the sort of position-dependent shift of the scalar. So this is a symmetry that relates fermions to scalars, or it ties together fermions and scalars, right? It doesn't relate them. The shift in the fermion is given by the fermion, the shift in the scalar is just a field-independent shift. But the symmetry links the fermion and the scalar. And in particular, what it does, it links exactly this vertex correction to lambda with the wave function randomization of psi. Right? For the symmetry to be respected, what I need is that the wave function randomization of psi is tied to the shift to the correction in lambda. And it's exactly this combination that makes it the beta function for the coupling constant that's guaranteed to always be the same between the vertex and the fermion. So we would be saying this, what we found at one loop, this vanishing of the beta function at one loop, is actually guaranteed to all orders in perturbation theory by this novel shift symmetry that combines the time-dependent rotation in psi with a position-dependent shift in phi.
Sorry, why is the conclusion just perturbation theory? If this is a symmetry,
I presume it should also be true in non-perturbative theory. I just, all orders perturbation theory sounded really strong, but that I'm not quite sure whether I can justify this formula. It's certainly this relation between delta lambda and delta c psi, that should be true completely non-perturbatively. So the wave function renormalization of the fermion is related to the vertex correction by this formula that delta lambda is equal to half this lambda times delta psi.
I was just thinking,
like the broad identities you get in gauge series, right? In gauge series, we have exactly the same statement. There's a wave, the gauge invariance in the gauge theory ties together the wave function randomization of the charged matter with the vertex correction for the gauge coupling. That's a very similar broad identity here. So we have a symmetry that ties together two of these C factors that appear when I renormalize myself.
But did I understand correctly that the transform? If you can go on the next slide that you showed. I mean, the transformation here depends on lambda. So if that's the symmetry which has lambda there, then lambda cannot change, because if you shift lambda, if lambda changes, it will change the symmetry because the transformation depends on lambda. So that's why it's exactly marginal. I would think, even non-perturbative.
Yeah, it ties into the wave function randomization of psi.
Right. But I mean, just let's say that it flows to some other Lagrangian, it's on a different scale. It clearly cannot change lambda, because changing lambda.
If you look at my interaction factor, right, the important thing is if in my interaction vertex picks up a large C factor that comes with a lambda, and then the inverse C factors from psi dagger psi, then this combination lambda psi dagger psi, I need lambda psi dagger psi to stay untouched, so that if I shift my phi by alpha over lambda, then that term always spits out the same alpha factor. And if my interaction vertex spits out alpha dx dy phi, and for that I need that lambda psi dagger psi stays not renormalized.
Right. But it sounds to me like it's a non-perturbative statement. But maybe
I think that symmetry is non-perturbative. So I think what's non-perturbative is the relation between the wave function renormalization of psi and the vertex correction. So the renormalization of lambda and the renormalization of psi is linked to each other. That should be non-perturbatively true.
Thank you.
And presumably that's the same as saying the beta function vanishes non-perturbatively. I was just not 100% sure and didn't want to say anything wrong, but you're probably right. Here are the things that I didn't talk about. I have one slide on each of them just to whet your appetite. You can try to realize this all within string theory. People have a long history of kind of realizing field series in string theory. For supersymmetric field series, it was super useful because a lot of their properties get sort of geometrized by embedding them in theory. If you look at this, in particular, the foliated field series, that's pretty much already the theory that living on a stack of d-branes. So you can write down like some lattice of d-branes, and you can argue more or less straightforwardly that this realizes like a supersymmetric versions of these foliated field series. You can get also these exotic Seiberg-Schau-like series if you have like matter where you have the kinetic terms basically being generated by interactions of nearby stacks of branes. And that would be a whole nother talk, and I chose not to give that talk today. And then the other thing that we still study is like fracton QFTs with boundaries. When people study topological phases of matter, they found like a lot of the interesting physics is buried in when you want to study the field theory with boundaries, not just as it stands. So you might wonder what's happening with fractons. And we use these continuum field theory descriptions in order to try to count ground state degeneracy if you don't live on a 3 torus, but like on a 2 torus times an interval. And even though this is sort of obvious in hindsight, we kind of got surprised by the following fact if you do this. Even so, all we are doing is we're messing around with boundary conditions. This already affects this naively extensive part of the ground state degeneracy. And you would have thought boundary conditions only mess around with sort of subleading terms in the large volume limit. But the ground state degeneracy in the torus was sort of this n to the 2lx plus 2ly plus 2lc's. And this 2lx and 2ly is for the simple set of boundary conditions you can kind of impose changes to lx plus ly. So the extensive part of the ground state degeneracy changes due to the presence of non-trivial boundaries. There's still lots more we want to say about this, so we're still working on trying to understand the general patterns for boundaries, but this is also something that's sort of rather peculiar. Okay, that's all I have for today. I think we still just scratched the surface on this novel field series. Now, you surely, given the name of your seminar series, one could wonder how to do this in holography. There's clearly lots more to come. Whether this is useful for anything, I don't know, but it clearly expands our horizon and kind of teaches us, I think, really new things about all the fancy things quantum field theories can do if you really think through the details of these sort of new constructions that we are forced to take serious because of these fractal lattice models. Right. With this, let me end. And maybe I stop screen sharing so I can actually see people who might have questions.
Thanks very much, first of all. Yeah, please ask questions.
See, lots of people came in towards the end of my talk. So this is all this pure lost souls who thought that I talk at the regular.
Yeah, but we have the recording, so that's good. Tin, yeah, you raised your hand.
One question came to me. If you have non-qubit lattice symmetries, is there some models in continuum that capture those? Because then you wouldn't have kind of x and y are not distinguished coordinates. So how do these derivatives look like?
Right, so this is a good question, right? So clearly the theory has sort of baked in some sort of foliation structure. And can you write down series which have different foliation structures, not where the leaves are kind of nicely arranged in some cubic lattice? In this in-between language, the foliated field series, people can easily do this, where they can write down, because all they're doing is writing down continuum field series on the sheets, and then they can arrange the sheets in any way they want for these genuine continuum field series, these Seiberg-Schau-like field series, or sometimes people call these exotic field series. Different rotation symmetries would give you completely different field series. So this is, I think the general structure still has to be explored. And there's also certain fracton series, certain lattice models that people haven't found yet a place of how to write down in a continuum language. So this is, it's not like people already know how to write down the most general theory in this spirit. There's clearly, there's part of the sensitivity to UV scale. You're definitely sensitive to this foliation structure and how to best write this down. Like how you could ask, like, how can I couple this to background fields, right? There's some sort of dependence on the background foliation structure. There's some if you write down this foliated field series, there's some sort of field which tells you how these planes are stacked up, whether they're kind of regularly stacked up along a cube or whether they're stacked up in some sort of curved pattern. I don't know how to write down the exotic field theory, which depends on like some arbitrary foliation field. There are lots of papers about this out there, but I don't think this has been completely settled.
Thank you.
Any other questions? Like, I would have one silly question, because if you've shown that you can break symmetries in at least one of your examples, right? And like, I was wondering, what about quantization? Do you think there's a room for anomalies breaking symmetries in these systems?
There's certainly interesting anomalies in the system that they have been sort of analyzed. I mean, people found a lot of these Topf anomalies, right? Sort of where you have like some mixed anomalies between two different global symmetries. So there's like Shuheng Shao has a bunch of papers on anomalies in the systems. But no, if you're asking about like some real, like sort of the series inconsistent type of anomalies where you have gauge interaction, there's some sort of gauge symmetry that's anomalous, and therefore you need to throw your theory away. You clearly need to write down more complicated theories, right? These three theories, they can have some interesting Toft anomalies, but they don't have like some gauge anomalies or something like this. But no, clearly anomalies do happen. So if you study more interesting theories, maybe more interesting anomalies.
Mm-hmm. Any other questions? Well, okay, we already had a few during the talk, so let's end the recording here, and thank Andreas again. Thank you very much, and thanks to everyone who participated.
Thank you.
See you all next week.
Thank you.